Right. Hello, everybody. Yes, if you're watching this live, that's brilliant. Thank you for joining. If you've got any questions, please type them in the chat during the session and I'll get to them at the end. If you are watching this recorded, please feel free to email me at the end if you've got any further questions. The point of these sessions is to provide you with enough images and pictures and things like that to create your own mind map. So I have tried to put everything on these sheets, but then it's down to you to edit and reduce and to create your own personalized version of it. So I will go through the whole topics and things like that, and then you can go away at the end and edit it, but then also use it to answer exam questions. Okay, so it is summarizing your information, highlighting the bits you have to remember, and then you use it to apply it to questions. Okay, so this isn't the only thing you need for revision. You need to do those exam questions as well. Okay, so we're doing rates of reaction, equilibria, and organic. Okay, so we will start with rates of reaction. I really like this module. This one. It's one of my favorites. Don't know why, it just is. I just like it. I think it's because there's lots of practicals in this. So we'll start with the practicals, okay, and the equation. Excuse my bad zooming in of things, but in this top left-hand corner, I have put 3 images here, okay. These should remind you of the practicals you did. So what it is about rates of reaction, you have to, it's like physics with speed. You're measuring how quickly something happens. So what you've got to do is measure either how quickly the reactants go down or how quickly the products are formed. And this can be in, divided by time, obviously. This can be in the form of mass. So you can watch the mass go down. You can collect the gas if there's a gas given off as a product, and that's that one there, or you can watch it's light. So we've got a practical here where when the reaction happens it goes cloudy, so you watch until you cannot see the cross anymore. So there's 3 different ways of doing your rates of reaction, and I have put videos here, video links to all the required practicals for these 3 parts here. So all the links there, I highly recommend watching the required practicals. Okay, I've just realized that I think should, if there's any problems with the links to these, then let me know, but that shouldn't be separated like that. I think that should be like that. If there's any issues with the links, let me know, but if one works, then you'll get links to all of them. Okay, so sorry, that's just copied and pasted in the right in the middle of a link there. But yeah, first of all, please be aware of those 3 required practicals. They are quite popular, and tonight we are, well, there is another live session on paper 2 required practicals, which is this part of this. That's actually tonight on the 16th at 7 o'clock. If you want to join with that one, we go through a bit more detail about those practicals. If you're watching this after the 16th of Feb, then they are on the website and you can purchase the recordings of those as well, just to complement this. So that's the first part. We go across, and there's some other little things you need to remember. Let's look at equilibrium and energy changes and reversible reactions. So first of all, be familiar with this symbol here. That means it is reversible. So that means that your reactants and your products can be in a state of just change all the time. So it could be going one way, it could be going the other way. And what's really common is that one way is endothermic, one way is exothermic. Okay, if you don't know what that is, recap on endo and exo. But chemistry there, endo is when energy comes in and it cools down. Exo is when they give off heat. Now these 2 here, this one with the ammonia is a typical one, a typical example of a reversible reaction that you will be introduced to. And also the copper sulfate, which is hydrated. Hydrated means just got water in it. So if you take that water off, then it just becomes anhydrous. So be familiar with those names as well. And then to put it back to hydrated copper sulfate, you just add water and it's exothermic. Okay, so that's one of your main examples for reversible reaction. I've put this picture here. I'm not going up. I want to zoom in. Oh my goodness me, it's just jumped across the page. Just wanted to zoom into here. I quite like this picture here because it's got difference between an open and a closed system. If you're not sure what open system is, it just means it can transfer to the environment. Closed system is when it's just trapped, basically. So be familiar with that. And the iodine will behave in a different way according to whether it's closed or open. Okay. So in a closed system, it will just be in eternal state of reversible reaction. Okay, so I just thought I'd add that one. If you put this equilibrium equations onto a graph, it would look something like this. So when the rate, so you got a forward one is going from left to right, a reverse one is going right to left, just to clarify. When you're measuring those rates based on the required practicals that we have just briefly gone through, but you will obviously have to brush up on, the two rates, if it is a reversible one, will meet and plateau out, and that is where it's reached equilibrium. So therefore you've got a balance of, if you took the substances and analysed what was in that test tube, you have bits of everything. You'll have reactants and products all mixed together, and it will be at equilibrium. So it'll be constantly going back and forth. Okay. With the copper, hydrated copper and anhydrous copper, remember the colours. Okay, that might help you. So anything to do with copper is typically blue, but here you've got the anhydrous copper, copper to 3 sulfate, which is white. Okay, know the colours of it. They're both heated tested. Blue crystals will turn into white powder and a clear colourless liquid, which is the water. Okay, be familiar with what those particular ones look like as well. With reversible reactions, the higher people, so not foundation, higher students, as well as separates, obviously, you will need to know about the Le Chatelier's principle. Okay, so with reversible reactions, you need to know how concentration, increase in reactants or increase in the products does to the direction of the equation, the temperature, and also the pressure. Okay, one thing they haven't added here is moles as well. Need to think about how many moles. With moles, it's always favours the side of smaller number of moles, smaller particles. Okay, pressure favours the side with smaller number of molecules for the same reason, it's just space. Temperature favours endothermic reactions. If you lower the temperature, it favours the exothermic. Okay, that makes sense. So endothermic requires energy from the environment. If you increase that temperature is going to go straight into the reaction and favour the endothermic direction of that equation. And typically in the exam question, they will tell you which way is which for exo and endo. So don't panic about that. Concentration favours, if you increase the reactant side, obviously that will favour transferring it to the product. So favours the forward reaction. If you increase the products, it will favour the reverse reaction. Yeah, okay, muddled up then. So that is basically Chatelier's principle. Okay, so be familiar with how they favour the direction of the reaction, forward or reverse. Yeah, down the bottom here. So with reactions as well, which I've put down here, I'm actually going to move that one over there. Where's my surface area one? Here we go. This goes with the surface area one there. Hold on, let me move across a bit. I've put a series of graphs here to show what happens with, again, like different factors when it comes to your rate of reaction and how you can increase or how it's decreased with the rate of reaction. So first of all, high concentration. The higher concentration, the higher frequency of collisions. So you're making that container completely full of your reactants. So it's like a busy classroom, basically. And if you ask the students to run around, they're going to hit each other. If there's only 5 students in the room, you run around, you're going to avoid each other. Reaction will only happen if your reactants collide and hit, and they have enough activation energy to enable the reaction to happen. Okay, so increased concentration, you will increase your product. If we go across, if you increase the pressure, i.e. you have the same number of particles, but you're enclosing the volume that they occupy, you are actually increasing the concentration. Basically, you're squashing them all together. So they will collide more frequently. Use the words frequent collisions. That always helps in your answer. Temperature, bit of particle model here. Here we go. You're increasing the temperature, you're increasing the kinetic energy, you're increasing their speed. So they're going to buzz around a lot quicker. If you walk around a classroom, a crowded classroom, you're not going to collide. If you run around a crowded classroom, you're more likely to collide. Think about it like that. Surface area. This is also another aspect of the rate of reaction practicals you might do. You might do hydrochloric acid with marble chips and then as powder. So you're increasing the surface area. That is basically showing that the more surface area, the more likely there is going to be a reaction, because you're exposing more of the reactants that are going to react. So if you have a massive marble chip, you can only react what's on the outside. If you break that marble chip down, you've increased the surface area, so there's more likely that a reaction will happen, so you increase the rate. And then effect of a catalyst. A catalyst works by providing a surface area that the reactants can bind to, and that surface area, or that whatever they're attached to, will provide an alternative pathway for that reaction to happen that will require less energy. So if you look at your, bear with, hang on, it's up here, I think. Yeah, there we go. So your activation energy with catalyst here. You will lower the amount of activation energy. Please know how to label these graphs, your energy profiles, okay? So your activation energy will lower because you have got that catalyst. Don't forget, transition metals, separate science people, this is, all your transition metals do act as catalysts. So it, for example, iron will act as a catalyst in a chemical reaction, providing a different lower energy pathway for that reaction to happen. Oh, look, it even mentions iron there with the Haber process, which is another reversible reaction with gases in it. Again, that's often linked to the Chatelier's principle there. So the Haber process, lots of gases involved, which is, let me just look up here. It's not that one. Where is it? The ammonia one here. That's a solid one. But the Haber, I thought it was a Haber one there, has all the gases involved. So maybe if that is one that you're not familiar with, just get that chemical reaction written in here as well. Maybe I'll add that as well and amend the sheet. Okay, so iron beads are used to increase surface area, available for catalysts. Yeah, normally only small amounts of the catalysts are needed for the effect. Okay, so yeah, another helpful hint, remember your energy profiles, endo, exo, that might get incorporated in an exam question in this situation here. Okay, collision theory, that is what I was mentioning before. You need your reactants to actually collide, and you need that amount of energy, activation energy, for that reaction to happen. So that links in the collision theory. And then for hires, okay, not foundation, after calculating rate of reaction, you need to consider moles. Okay. If you're working in mass per unit per ton, then the process is such and such. If you're working in volumes per unit, it is this in bulk. Don't forget, gas is your 24 decimeter cube. 1 mole is 24 decimeters cubed. Okay, here they've done it centimeters cubed, so you times it by 1,000, and that's how you get to centimeters cubed and decimeter cubed. Okay, so I've just added that bit there. So if you can't remember that, go over it and or just add that to your mind map. If we go back out, I'm just going to look, make sure I've covered and talks about everything on rates of reaction. Yeah, the only thing I will add is the Haber thing. Oh no, hey, an example of a dynamic equilibrium is, yeah, oh, I have, but I haven't put the equation there. So ammonia is NH3. So there we go. This is an example of dynamic equilibrium reaction. So that's your Haber process. You could bind hydrogen and nitrogen together to get ammonia, and they're all gases. So then that links with the Chatelier's principle there. Okay. What's the most common one used to talk about and ask questions on? Go away, Bark. Right, Bar, you are really irritating me. You go up there, thank you. Right, let me go to the second page. So alkanes. So I've created a mind map, lots of information here about alkanes. Do not just print this off and use it. I have deliberately added this information and all these wordings for you to then dissect and crop down. Okay, I will go over things though. But again, I have over exaggerated with the writing. This is not a mind map. As it is in its format here, you now need to select what you need to revise, okay? So if we go to the alkanes, this is your organic chemistry. I really thought, I think I might sneeze, you know, try not to, not good. So this is all part of the organic chemistry. So we've covered rates and we've covered equilibrium. Organic is all about your hydrocarbons. Okay, and the different functional groups on that. So know what a functional group is. It's a group of atoms, converts certain physical and chemical properties onto one molecule. So we'll cover those different ones. It's more specific for like separate sciences, so which is the last sheet where it just goes crazy. It's so much you have to sort of remember. But for combined foundation and higher, this is all relevant to you. Know the word homologous series. Homologous just means, like for alkanes, you've got, this is a homologous series. They've all got the same pattern, same atoms in there, but they just change in the number. Okay, so it's just a series of hydrocarbons, basically. Every carbon, with alkanes, remember your, I don't know why that's up there. General formula. I've got that down for alkenes, but I don't think I'll put it down. It should be somewhere in one of these pictures. Oh, here it is. I knew I had it somewhere. So can you see here? Let me just zoom in. This is a typical one marker. They like you to specify what the general formula is for alkanes, and that is carbon, CN. So that's the number of carbons. H2N, so you multiply the carbons by 2 and plus 2 because you've got the 2 hydrogens at the end. Know how to write your hydrocarbons. So there's different ways of writing it. Display formula, molecular formula. So this is your display formula, and this is your written or molecular formula. So you write the actual number. You can do structural, so you can write it out like this, and when it gets to separates, then you do sometimes see them written like this. The display formula structure of pentane, so it just gives you an overview of what the different ways of writing out these hydrocarbons can be requested, basically. Generally speaking, most often it's either display or molecular. Okay, when it gets to separates, they quite often put it as structural formula like this. So if you struggle with that, just draw it out as a display formula. That's what I do. I find it, I'm a visual learner, so I find that a lot easier. Oh, what did I put this one in here? As you move up the fraction, oh, that got to go. That goes with this over here. Let me just put that over there like that. Okay, right. Let me move over again. Then we've got up here. Let's go in. So again, we've got homologous series. So I've added a little bit on here. This table is important. Okay, you might get data like this. You don't need to memorize this at all, but you do need to know at least the first 4 to 6 hydrocarbons in this homologous series. Okay, they've got all the same functional groups and they follow the same general formula. They all differ by a carbon and 2 hydrogens, okay, because you're just increasing the length of the chain. They do ask about the physical properties like the boiling point. So what's happening with the boiling point? I might even, oh, can I add? Oh, can I don't know if I can draw on that. Can I draw on that? It's intermolecular forces. I might need to annotate and then you can note down this. So it's your physical properties. Is it going to allow me to do it? No. So with the boiling point and melting point, what is happening when you have you're going from a solid to a liquid? This is relevant for fractional distillation. So your chain, so depending on how long your chain is, will link how many intermolecular bonds there are around it, linking it to other hydrocarbons. Okay, so these are your intermolecular forces. Now, when you have very small hydrocarbons, there's not many intermolecular forces around it, joining it and binding it with other hydrocarbons. So the amount of energy needed to break those intermolecular forces is small, hence why they have a lower boiling point or melting point. Okay, boiling points and melting points are all to do with how much energy is required to break those intermolecular forces. So obviously, as you get longer chains, there's more intermolecular forces to break, more energy is required, and therefore you have to have a higher, well, it results in a higher boiling point. And that's pretty much what fractional distillation is all about. Okay, it's all about how much energy is required to break those intermolecular forces. Clear that, do that. Okay, so remember that. Yes, crude oil. So our hydrocarbons come from sources that are from dead plants and animals, made millions of years ago. It's yet finite, another key word to remember. Finite resource means it will run out, basically. Infinite means it's not going to run out. It's the opposite. So yeah, it's going to take a long time to get back that crude oil, and personally it should stay down there because that's its carbon sink. Anyway, right, millions of years, yeah, pressures and temperature, yeah, but many of the remains of biomass, mainly plankton that was buried in mud. So just a little bit of information about composition of crude oil. And then we've got our lovely display formulas, structural formulas, also display structural formulas and things like that. So that's another little table there. I'm going to just ignore cracking at the moment because that's when we, oh, shall I do cracking yet? Let's do cracking. Let's do cracking. So down here, there's a little bit on about cracking. Now, cracking is a process where, actually, no, let's do, let me just do that. I want to do fractional distillation first. So maybe, I should really put cracking with fractional distillation. So there you go. You can edit that yourself, but let's do fractional distillation because I was kind of talking about that anyway. with the intermolecular forces. So let's go here. So this is a structure of fractional distillation. Know your fractions here and what they're used for. That you do need to know them. As you move up fractional column, temperature decreases, so the compounds with higher boiling points come off lower down the column. So the separation of crude oil, just imagine crude oil is just a whole bag full of different lengths hydrocarbons. So we have to separate those out. So the very small ones like methane, etc., have a very low boiling point. So they actually become gas or vapor and will rise right up to the top very quickly. Those that are really, really long, like diesel and fuel for like power stations, etc., like that, and even bitumen, they have a hugely long chains, therefore a very high boiling point, and they will stay sort of liquidy and then get siphoned off down the bottom. Okay, let me just check. Yeah, and they've got single bonds, yes. So that is basically fractional distillation. Now, questions come about with that because obviously crude oil, it is made up of different fractions. We use like gasoline and diesel far more. It's in high demand compared to other fractions of crude oil. So therefore, what cracking is all about is breaking up maybe the longer chains of hydrocarbons, that fraction there, and cracking it up and breaking it down into smaller sections that will fit the petrol and the diesel demand. So how they do that, please go across and then down. Oh, it's got the wrong way. How they do that is two processes. You can either do catalytic cracking, quite high temperature, so it needs to be at high temperature. It just runs it, pass over a hot powdered catalyst of aluminium oxide. It breaks down all covalent bonds. So hydrocarbons are all covalent bonds. That could link in with the exam question. They could start talking about covalent bonds and then go on to hydrocarbons. Beware. Yes, thermal decomposition. So thermal decomposition is when it's easy to recognize because there's only one reactant. And it is literally, it just decomposes, it breaks down. And that's what cracking is. It's a thermal decomposition. So you need high energy, thermal, and then it breaks down. So yeah, you use a catalyst, which is your aluminium oxide, or you can use steam or thermal cracking. So it's carry out slightly higher temperatures and produce unsaturated carbon. The vaporized hydrocarbons are mixed with steam and heat to a higher temperature, which then induces your cracking. The other thing you've got to remember about cracking is that you will always produce one alkene. Okay, we haven't talked about alkenes yet, but because of the number of hydrogens, you are never going to get to alkanes. And always double check that. It's like, think about it as a balanced equation. Well, however many carbons and hydrogens go in, you will have to have the same amount going out. So that's why there's always an alkene. You can't predict the size of the cracking. You could have here, we've got 8 and 2, but you could have 6 and 4, 7 and 3. It doesn't matter. So when they ask what the products are of this, a decane, you can have any number of combinations. You can have 3 different products there, doesn't matter, but as long as they all add up to the same number as the decane, you're fine. Okay, so think of it as a balanced equation. So that's catalytic cracking and steam or thermal cracking. That's how we do it. And the main point is because we have the demand for smaller fractions of crude oil, so that's why cracking is needed. Let's go on to combustion. I love combustion. That quite often is a balanced equation involved with this. Okay, and you need to know your product. So know the typical equation for combustions of alkanes, and it is your methane gas. Incomplete, I'll put a little diagram here. You can have, it's really difficult to do a balance equation. If they've given it to you, fine, you can balance it. Because the issue is with incomplete, which is your lack of oxygen, you can get carbon monoxide, you can still get carbon dioxide, but you can also get carbon, which is your black sooty smoke when you see fires and stuff. That's just plain carbon. Again, just they can be tricky to balance. I personally never would put 3.5. Always for that, I would double it up to 7 and then make that 6 and then make that 8 and then 2, obviously, for the methane, propane. My brain just went then. So know your formulas here and know about balancing equation. I do have a video on balancing equations if you are interested. So yes, that's the only thing about combustion really that I would recommend you know about. And then what have we got here? What's in this bit here? Petrochemicals. Oh yeah, I put a little table there of all the different fractions and their uses. A little bit of information there. Edit that as you wish. And oh yeah, the physical boiling points of them. It's just a visual showing there of how the boiling point increases. But you could also be asked about, I love this word, viscosity. Oh, brilliant word, brilliant. So basically, think of honey. That's what I was doing. Just think of honey. When you've got high viscosity, it's really thick and not very runny, and that's your long hydrocarbons. Okay, think about like tar for roads and stuff. That's your bitumen stuff. That's your really long hydrocarbons, and it's got really high viscosity. And then flammability. So smaller hydrocarbons are more flammable. Again, link it. Your gas that you get from your oven, that's methane gas, also from cows' bottoms. They're the reasons why we've got global warming, but anyway, highly flammable. Okay, so if you picture in your head the gases methane, they're highly flammable. As they get longer, chains, that is, the flammability decreases. Okay, because obviously if you've got tar on the road, which is your bitumen, you can't really throw a cigarette butt out the window, not that you want to anyway, but you see people do that, probably inflame the whole road. And so they're not very flammable, basically. Yeah, so be aware of those words and those physical attributes. Word as well. God, I'm saying lots of lovely words today. But that's about it really for alkanes. And that's pretty much it for combined science. So those that are doing combined science, take those first 2 sheets, edit them, create a masterpiece. You're all good. Okay. Separate, you've got this sheet as well to actually, well, I think you might end up with 2 sheets of this, but again, there's lots of writing on here that you need to condense and, pick out those key words. Okay, so please don't just print this off, as I said before, use it. But what I have done, I've created my own little mini mind map of, maybe it could be a structure that you could use when you're editing this. Okay, well, why is it not over? Why is it over like that? Oh, okay. I obviously haven't cut and pasted that brilliantly. Anyway, right, this one here, So what I have done with alkenes, I have done my little mind map. So there's different sections of alkenes that you can remember, and maybe putting it like this might help you. So we're going to look at, again, combustion of them, addition reactions. So you add different things to them and what happens when you add different things to them, like water, halogens, and hydrogen. This is linked in your functional group, so you can build up and create alcohols by combustion, sodium oxidation, carboxylic acids, how we make weak acids and esters, and then it goes on to polymers, how to create polymers, natural ones, DNA, starch, proteins, as well as additional polymerization and condensation polymerisation to create nylon. Okay, so that's kind of like a really summarized version of everything you need to know about alkenes. So if we start at the top here, again, general formula. Again, it's different from alkanes because you haven't got the +2. So this is a typical alkene. It's always got a double bond somewhere. Okay, that means it's quite reactive. Doesn't want a double bond. It wants to be single. Okay, it's not very good for post-Valentine's Day, but anyway. You can identify an alkene using bromine. Okay, the bromine will attach and, well, unwind that or remove that double bond and attach to the carbon, forming dibromoethane. Don't need to remember that name at all. And what that visually looks like, if there's no change, that means the bromine hasn't reacted. Alkanes do not have that double bond, so they are not reactive. Okay, alkenes have got that double bond, so they will react, produce this dibromoethane, and become decolorized. The bromine is always brown. Okay, so it's a way of identifying if you've got an alkene, and that does come up in exam questions. Okay, and again, nice little summary table there. We're going to move across combustions of alkenes. Again, it's full combustion, incomplete combustion, produce the same things again. Don't forget to balance them. Okay, that's what you would learn from that. Do not forget to balance them. I'm not going over it again. It's the same principle as what happens with alkanes. Okay. Then we're going to go on to, you've got, with the alkenes down here, you've got addition reactions. So what happens when you add water, halogens, which is the bromine, and hydrogen? So here we've got hydrogenation. So you just add hydrogen and look, you end up with an alkane. So nickel catalysts, don't forget most transition metals are catalysts. So nickel is a transition metal, and then it will change into an alkane at this point because it's just hydrogen. Hydration is adding water. What happens when you add water? You produce an alcohol. This is one of your functional groups you must remember. Okay, so and this is over hydrogen phosphate. Does it say over here? Does it say acid catalyst? Yeah, concentrated phosphoric acid. Okay, so that is on there. I'm just checking that word was on there. Really high temperatures, high pressure as well. Okay, these are the sort of factors that you could be asked about, and you might have to describe if you ask what happens when it reacts with water. Okay, so you produce ethanol. So let's look, ethanol, O-L, but it's actually O-H. I don't know, it's one way of remembering the functional group, I suppose. It's going to make sure I've mentioned everything. Reactive ethene. The contents are transferred to a condenser where ethene is separated easily as it has a much lower boiling point. Ethanol and water are separated afterwards by fractional distillation. So again, they're separated by their boiling point. Okay. So remember, water, you add water, it turns into an alcohol. What have we got here? Alcohol functional group here, side chains. So you've got just the OH, and you've got all your different alcohols there as well that you can produce. It's very similar, just put an ol at the end. So the ene is ol. Good old English language. Production of ethanol by fermentation. Hang on, let's zoom in about there. Oh, it's a bit blurry. I'm sorry about that, but when you enlarge it, it should be a bit better. I should try and enlarge it a little bit. Yeah, it's a little bit better. Yeah, ethanol is most important. Alcohol, it's in alcoholic drinks. Brilliant. Also used as fuel for cars and as a solvent. The mixture of fermented, so yeah, you can, it can be produced by fermentation where sugar and starch is dissolved in water and yeast is added. So there's another way to produce ethanol, basically. Exam tip here, fermentation is an anaerobic process. Oxygen is not required for ethanol to be produced by fermentation. So there you go. That's because you've got sugar in there that has the oxygen. So there we go. If you ever wondered where the oxygen comes from, it comes from the sugar. Carboxylic, was this one of the, where's my little diagram? Up here somewhere. No, down here, it might be across. Hang on, bear with. Just, yeah, halogens. Yeah, we've done the halogens, done hydrogen, done water. Okay, so the next one is, yeah, we're looking at the alcohols now, combustion, adding sodium and oxidation. Okay. And then it's carboxylic acids. Okay, so we're going to just focus on the alcohols to start off with. Okay, let's finish off. And we're done. So it says reactions of alcohols. I'm going to just expand this a little bit more for you. Alcohols are colourless liquids. They are actually, yeah, that's one physical feature of alcohols. They are transparent. You can't see them. So uses fuels, comes up fuels and solvents for alcohols. It's all good, as well as drinks. Let me just check what else is saying. Right, alcohols react with sodium, metal, produce hydrogen gas and a metal salt. Okay, know this equation. So sodium plus any alcohol turns into the sodium salt of that alcohol plus hydrogen. It's the same as when you react a metal and acid. Okay, remember that it's a metal and acid produces a salt and hydrogen. Alcohols undergo oxidation to produce carboxylic acid, which we're going to go on to in a minute. They do this using, so what happened to wine when it was left open, microbial oxidation of ethanol, produce a weak solution of carboxylic acid. That's why your wine sometimes tastes like vinegar if it's off, because it's been exposed to oxygen and made bacteria, and they have the bacteria has produced that ethanoic acid, which not nice at all. So yeah, it's like just tastes like vinegar and water. Just might as well just get your chips out and put it on the chips. The acidic vinegary taste of wine left several days due to the presence. Yeah, there you go. That's why you must, if you don't finish your bottle of wine, put a stopper on it, and that should preserve it for a little bit longer. Okay, so that's your reactions with alcohols. And now we've got the next link up is the carboxylic acid functional group. Okay, so we have, again, your functional group here is COOH. Remember that. I'm just going to zoom in a little bit more on this one. So they differ by one carbon hydrogen group. They show graduation of physical properties, viscosity increasing, same as your alkanes. They have two similar chemical properties. So you've got to remember the functional group, COOH, but you've got to remember the arrangement as well from that carbon. So you've got a double bond to an oxygen, and then you've got the OH separately. Okay, so it doesn't go like COOH. It has to look like that. Okay, that's the general formula for it. The first four carboxylic acids are these. Again, a nice little visual representation of how they're supposed to be drawn and how they look. Okay, so please note that. That's really important. Then you've got your, as we said, reactions with carboxylic acids to produce weak acids and esters. So the carboxylic behave like other acids. They react with metals. There you go. And carbonates, the same as, I can't remember what module it is, but a previous module, paper 1 module. They take part in neutralization, producing salt and water. So it links in that reaction with metals from that module quite nicely. The salts formed by the reaction carboxylic acids will end in anoate. Okay, and another name to remember for another salt. And know how it does start to look a bit complicated, the written format of the formula. I always personally have to draw it. When it comes to things like this, like the written one, that's absolutely fine. But if I draw it and then I can write it out in that format. Okay, that's just my way of doing things, making sure I avoid silly mistakes. So I recommend that. In the reaction with carbonates, a metal, salt, water, and carbon dioxide. Yeah, always remember the carbonates. You've got that extra carbon, so carbon dioxide is produced as well as water. Okay, and if it is just the carbonate and metal on its own, it is just hydrogen. If it's a metal hydroxide, you've got water. If it's a carbonate, you've got water and carbon dioxide. Bit of a revision for other modules here. So to produce an ester, you have, for esters are compounds with a functional group R, which is more carbons, and COOR. So how that's drawn, you've got ethanoic acid and ethanol. You've got to remember where the water comes from. Okay. They sometimes ask you, draw around the hydrogen and oxygen that get used to make water, something along those sort of lines. So remember, it's the OH from the ethanoic acid and the H from the ethanol. Okay. And then they bind together, producing water. So this is a condensation reaction, because you're producing water, condensation of water vapor. And then you've got ethyl ethanoate. It's got no mate, it's just an ethanoate. I don't know, it's stupid little ways to remember the names, I know. Yeah, and it just binds with the oxygen, and that's just how they combine together. Okay, so try and keep it simple. Think about it in a simple way. All you're doing here when you're reacting alcohols and carboxylic acids, oh my goodness, that's a horrible word, esterification. I prefer viscosity, it's much better. But anyway, that's all that's happening. You're reacting ethanoic acid, producing water, and just binding the two together on the oxygen. Don't overcomplicate it other than that. Higher tier only for carboxylic acids and as acids. Too much acids, however, they differ from other mineral acids. Let me just say hydrogen characteristic properties. So if you remember acids before, acid is basically the dissociation of the hydrogen ion from whatever source it is, the hydrochloric, sulfuric, or nitric acid. The stronger the acid, the more dissociation. Okay, carboxylic acids dissolve in water, but they only partially ionize, and they produce weak acidic solutions. So pH between 3 and 7. That's not acidic, that's neutral. Anyway, carboxylic acids form an equilibrium with their ions, but most of the carboxylic acid molecules are undissociated. So ethanoic acid, which is your vinegar, is only partially ionized, and ionized just means it's forming ions. Okay, and that's through dissociation. Okay, so how you draw that, you have your equilibrium, your reversible reaction. I'm just zooming in, but it's gone over to there, bear with. It's just here, yeah. So you have your equilibrium formula here. So it's just a constant moving between the two, linking in your equilibria content and knowledge there. Don't forget to write them as ions, okay? Same thing as before with hydrochloric. You've got positive hydrogen, and you just bunch everything else together minus the hydrogen, and you just add a minus on the end, okay? And 100 molecules, you don't need to know about this, but you need to know the difference between a strong and a weak acid. okay, and know that ethanoic acid or carboxylic acid is a weak acid and the reasons why. Okay, bit of revision from the last modules as well, like from before, so it's all good. Done the functional group, so I just want to go back to my little diagram. I think that was all about, that's all the carboxylic acids. I think what's left is just about the polymers. Let me just go out. Let me just double check. I think the everything else is on. Done all that. Yeah, I think all we have to now is go over polymers. So here with polymers, you've got how polymers are created. That's additional condensation reactions. And then you've got natural polymers, DNA, cellulose, starch and cellulose. I can't believe I've chopped all that off. I might have to go back and re-edit that. I'm really sorry about that. Because that should be starch and cellulose. Right, well, I will edit that. Do not panic. Okay. And then you've got condensation is nylon addition. Yeah, then you've got, nylon condensation reaction. So let's start with, where's additional polymerization? Condensation, polymerization. I think this was the first, this is the first one here. So polymerization here. So got to remember, polymers are long chains of monomers. You need to remember how to draw them. So a monomer is wrapped around with brackets, and the little n represents how many there are, basically. Typically, typically a monomer will always have a double bond because it's got to be reactive. It's got to react with something, and then it will attach to other monomers forming that polymer. So yeah, when you're representing that monomer as within a polymer, that's when you put the brackets around. So yeah, there's just some examples there. And know where these are found. So they're in resins, plastics, polystyrene, nylon, etc. Higher amino acids, that comes under your naturals. And then we've got that one there. I'm going to move all this around. We can read it. Amino acids. So yeah, you've got amino acids there. So your natural ones are DNA and amino acids, as well as starch and cellulose. Don't forget about cellulose. This is all about A-level biology, this is. So DNA, I might redo this one as well. This is looking a bit fuzzy. DNA is a natural polymer. They might ask about this. There's not, I can't remember many questions, but just be aware of them. You've got as well other natural polymers, starch and cellulose, all made up of carbon, hydrogen, oxygen. Well, proteins are polymers, natural polymers, so that's where your amino acids is. So yeah, hemoglobin would be a natural polymer. So are antibodies, because they're all, and enzymes, they're all made up of protein, which are long chains of amino acid, which is a polymer. So yeah, it's when it links biology. We're linking biology with chemistry here. We like it. Yeah, please excuse me, I will re-add these pictures to this mind map just to make sure you can read this a little bit more clearly. With this sort of part of it, you just need to know the examples. I think there's not much more. The only, I was going to say, the only sort of the chemical side of things is when you're looking at condensation reactions and how you produce nylon, or and looking at amino acids and what they look like, their functional groups. Again, linking in that functional group, know your different functional groups. So amino acids, for example, have the carboxylic group, the COOH. They also have amino to make the amino acids, and R is your what do we call it? The R group. That just defines what amino acid it is. basically. So my brain's the R represents the varying side group. Yeah, it doesn't matter, but it just changes. You've got 20 natural amino acids. So that R group determines what that amino acid is. But all the amino acids have an amino group, they have a hydrogen, and they have a carboxylic acid attached to them. Okay. Then how polymers, how proteins are made, that's what you've got to remember. So I'm going to just move that down there and enlarge this a little bit. As I said before, I'm going to redo these pictures because they are not very good. Or maybe I've just zoomed in too closely, I don't know. Similar to the carboxylic and acid binding, you are producing water, so it's a condensation. Condensation polymerisation just means you have produced water as if by magic, and that's because, again, you need to remember where that OH is coming from and where that H is. It's the same thing as the carboxylic acid and acid. It's from the carboxylic group, you've got the OH, and from this one here, it's the amino group hydrogen that it is grabbed. You then bind the carbon to the nitrogen. I have seen where they've asked you to draw around where the bond occurs, or this is the peptide link, I might call it peptide link in this case. So make sure you draw all around the nitrogen and carbon and whatever is attached to those specific ones. So that's your binding place, plus water. Okay, so every time those two bond together, you'll produce one water molecule. And this diagram down here, amide link or peptide link. I think this is just a close up. Yeah, so again, just showing, probably don't even need that, but I'll keep it on there anyway. But that's exactly the same as what is in that diagram there. And then the bit I've added to this one, I'm so sorry about these pictures. It's not until you go really close that you like realise how dire some of them are. I'm so sorry. I will redo them and re-add them to the folder. With this one here, this is your higher tier, two monomers together. Yeah, it just sort of summarises everything. Again, based on this picture, you've got for every, this is your ester link. So you've got peptide link here. This is your ester link. So condensation reaction, they use an example of what they're doing here, the an acid and ethane functional group, also monomers. So you've got, where am I? I can't even read it. One molecule of water is formed. We've done that because you produce it goes into more detail here. The water molecule comes from the proton from the acid and the hydroxyl ion OH, which is your alkali group from the other functional group. So this is a carboxylic acid and esters again. Yeah, so you've got your carboxylic acid group here and your alcohol, condensation polymerisation. Again, draw around that box around where the carbon and the oxygen bind and whatever's attached to the carbon there or the oxygen. If it's another carbon, you don't draw anything more, okay? I don't like these diagrams here, but sometimes they are represented like this, okay? So I don't like that, but it's basically cutting out these boxes here, the white boxes here, and that are the clump of carbon and hydrogen chains. So instead of writing out all those carbons, it's just represented by a box. That's it. Okay. The last thing I'm going to say, don't forget to learn about which one's a peptide link, which one's an ester link. Okay. Peptides, remember, proteins and amino acids, PP. Ester link is your carboxylic acid and ethane making an ester. Okay, to know the names of those, it might crop up, you might need to know. But that is pretty much it. So it doesn't look too bad. When you zoom out again, it doesn't look too bad, the writing. It might be okay. I think it's just because I zoomed in quite in. Oh, I can't even talk. I zoomed in quite a lot, but I will do this natural polymer one. Wasn't anything under there because it looks like I have cut off a little bit of the writing there, and I do apologize for that, and I will redo that one. Okay, right, a lot there for separates. I am so sorry, but hopefully I have summarized what you need to know, what you should be aware of, what the key things you've got to remember, and how some funny little ways of trying to remember things. Try and keep it as simple as possible. Sometimes students look at this going, oh my goodness, how much have we got to remember? But link it to other things like your neutralization, how acids react with metals, blah, blah, blah. Know your functional groups, how, you know, the peptide links, the ester links, etc., and combustion, incomplete combustion, blah, blah, blah. Just keep it simple. If I ask to see any mind maps that have all this writing on it, I'll be very upset. I have included it on here so that you can nitpick and take what you need to create your own mind maps. Use these pictures and diagrams to help. And I have given you just something to structure your mind map with as well, just with that, my little drawings there of how everything fits into place. Okay, but I hope that has helped. If there's any questions, I'm happy to ask now. I'm just going to finish by stopping the recording, but as I said, if you're watching this as a recording, please, if there's any questions, just give us an email. Okay, thank you.